So what have we been learning about with linear algebra? I'm going to talk generalities here. Though after I talk about the generalities, hopefully we'll have a little time for thinking about an example or two. You've got a system of linear equations. Say m equations and n unknowns. That's going to correspond to a matrix vector equation. AX equals B. If the system of linear equations has m equations and n unknowns, and A is the coefficient matrix for that system, meaning you're taking the numbers in the system and writing them down in a matrix, then A will be an m by n matrix. M rows go horizontal, left and right. You're counting how many of them there are, say m of them. N columns, okay? If m is bigger than n, m rows, n columns, m is bigger than n, then it's a tall and skinny matrix. More equations than unknowns. Think conceptually here in your mind with me. You can even draw a little picture if you like. If m is bigger than n, it's like a tall and skinny matrix for A. You could draw it like that. More equations than unknowns. If m equals n, that's called the square matrix. The number of rows equals the number of columns. You could draw it to look like a square. And if m is less than n, more columns than there are rows. Like a long and wide matrix, back and forth. You draw it more like this. Just in your imaginations, it's helpful to think this way. X, what kind of dimensional vector would X be? M or n dimensional? N dimensional. We write them as column vectors. We call it an n by 1 column vector. Do vectors have to be written as columns? No, they don't have to be. They can be written as rows. It's just more convenient to write them as columns here because it's more convenient to think this way in terms of A times X and defining what that means. It's just a convenience. You also can write vectors other ways, like with I hat, J hat, and K hat if they're three-dimensional vectors, for example. You can do this multiplication because the number of columns of A equals the number of rows of X. We are talking about a matrix times a vector here, but I can generalize that to a matrix times a matrix. B is a vector. If you multiply an m by n matrix times an n by 1 matrix, you got to get an m by 1 matrix. In other words, an m by 1 column vector. X is an element of Rn. X is an element of Rn, n-dimensional Euclidean space. B is an element of Rm, m-dimensional Euclidean space. In general, B is not necessarily the zero vector. In general, this is a non-homogeneous system. But B could be the zero vector. Then it would be a homogeneous system. If B were the zero vector, if I was trying to solve a homogeneous system, then I'd be trying to find what's called the null space of this matrix, which is the same thing as the kernel of the linear transformation. It's just different terminology. And what is the corresponding linear transformation? T is the domain Rm or Rn. Rn, because the input vector X has to be n-dimensional because A has n columns, that's why. So the domain of this transformation is Rn. The codomain is not quite the same as the range or image. Codomain is sometimes called the target space. What kind of vectors do you get out? It's Rm. It's like the B. It's m-dimensional. If we're in the case where m is bigger than n, so A is a tall and skinny matrix, that means the domain is a smaller dimension than the codomain. You're mapping from a smaller space to a bigger space. Intuitively, it can't possibly be onto, meaning there are going to be plenty of vectors in the codomain that are not possible outputs, meaning you're probably not going to be able to solve the system of linear equations. It's going to be inconsistent. If you got more equations than there are unknowns, in all likelihood, it's an inconsistent system. When you go to RREF, reduced row echelon form, for the corresponding augmented matrix, in all likelihood, the last row will have a bunch of zeros and then a 1 in the lower right corner, corresponding to 0 equals 1, which can't happen, contradiction, meaning the system doesn't have a solution. If you pick a random B, it won't, guaranteed. If you pick a special B, like a linear combination of the columns of A, then it will. Because the definition of A times X is to take a linear combination of the columns of A with entries of X as the coefficients. Tracking with me here? I know this is abstract ideas here, but you've done enough, hopefully, reading and examples and lecture watching, hopefully, that this is starting to make sense and you can think abstractly. Examples are great, concrete examples. We all love that, including me. But if you're going to be able to put everything together conceptually, you've got to be able to think abstractly. Abstract thinking unifies ideas. You have a question? Okay. Also, in all likelihood, but not guaranteed, it's probably 1-to-1 going from a smaller space to a bigger space. Probably there are no free variables. Probably the kernel is trivial. If we were solving the corresponding homogeneous system where B is 0, the 0 vector, well, for sure, 0 is a solution. Homogeneous systems always have solutions. Kernels are never the empty set. Kernel always at least contains the 0 vector. But in all likelihood, again, if m is bigger than n, the matrix is tall and skinny, going from a smaller dimensional space to a bigger dimensional space, in all likelihood, it is probably 1-to-1. There are probably no free variables. There could be, if I make these columns linear combinations of each other, for example, is one way I could do it. But probably random columns, it's going to be 1-to-1 and no free variables. In the case, let's go to the other extreme where m is less than n. Short and wide matrix like this. M is less than n. So the domain is big and the codomain is small. You're mapping from a bigger dimensional space to a smaller dimensional space. By the way, I forgot to emphasize the formula for T is T of X equals A times X. And do get that phrasing right. T of X equals A times X. That's the formula for T. N is bigger than M. You're going from a large dimensional space to a small dimensional space. Intuitively, some collapsing is going on. There's no way for such a thing to be 1-to-1. If you solve the corresponding system, there will be free variables. The kernel of the corresponding homogeneous system, if B is 0, will be non-trivial, more than just the 0 vector. If that's not intuitive, you want to work on making it intuitive by doing enough examples and thinking about it and doing your REFs and seeing, oh, there's free variables whenever A has more columns than there's rows. Because there can't be more pivot positions non-free variables than there are columns. So it can't be one-to-one. In all likelihood, if you got random entries, it probably is onto. Probably every B will have a solution. There will be a solution for every B. Because probably it's onto. Could I make it not onto? Yeah. For the easiest way to make it not onto is make A the zero matrix. Make all the coefficients zero. And then if you got a bunch of zeros on the left side and non-zero numbers on the right, there's no way there's any solutions. That'd be the easiest way to make it not onto. Make A the zero matrix, and this linear transformation maps every vector to the zero vector. But you pick random entries for A, it probably will be onto. No inconsistency in the system. In the square matrix case where M equals N, the domain and codomain had the same dimension. If the entries are random, in all likelihood, it's both one-to-one and onto. In all likelihood, the homogeneous system has a trivial kernel, just the zero vector. That's not the same as empty. The zero vector is always in the kernel. In all likelihood, with a square matrix, that's the only one. There's no free variables. And in all likelihood, the system is consistent. But again, I can make it examples where they're not. One example was on your exam. Let's do an example then. One example, it's not a very creative example, because the entries of the matrix are okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember that? Oops. So not a very creative example, but it does turn out by chance. I never knew this until I actually just tried it one day, that when you row reduce it, you get a row of zeros. That doesn't typically happen with a 3x3 matrix when you row reduce it. So what would that mean? That would mean thinking about corresponding augmented systems. If it was homogeneous, if it was all zeros on the right-hand side, it would be consistent because the last row would still be all zeros. There'd be free variables. Z would be a free variable. X would equal Z, Y would equal -2Z. You'd have a kernel that would be a one-dimensional line to the origin, but definitely non-trivial, containing more than the zero vector. If you had a non-homogeneous system with non-zero numbers on the right for an augmented matrix, in all likelihood, you'd get something non-zero in the lower right corner. I'll make up an example. Let's do that. Call it A augmented here. Make up a quick example. Use the same coefficient matrix, but some other numbers over here on the right side. And if I row reduce that, again, in all likelihood, unless I'm very unlucky, in the lower right corner, there will probably be a 1. Oops, a aug. Lower right corner, there is a 1. Now, Mathematica doesn't know that's an augmented matrix. It just thinks it's an ordinary matrix. So there certainly can be a leading 1 in that last row that corresponds to the right-hand side of the system of equations. This line is corresponding to the equation 0 equals 1, which can't happen. So if I assume the system had a solution and did all my row operations to try to find the solution, I end up with a contradiction. That means my original assumption that there was a solution is wrong. There is no solution. It's an inconsistent system. How could I make it have a solution? I could make this last column be a linear combination of these columns. I could add them, for example. 1 plus 2 plus 3 is 6. 4 plus 5 plus 6 is 15. 7 plus 8 plus 9 is 24. I have made this column vector in the last column of this augmented matrix be the sum of the columns of A. By definition, it's got to be in the image of the corresponding linear transformation. It's got to be in what's called the column space of this matrix. It will be a consistent system if I did my arithmetic okay. Yep, row of zeros now. There's a free variable. Z is still a free variable. X would still equal Z. Y would be negative 2Z plus 3. And Z would be free, arbitrary. The solution set would be an infinite set. There's actually infinitely many solutions. In parametric, let's go ahead and write that solution set in parametric vector form and emphasize something else here. So for this example, you're going to write the solution set in parametric vector form. This is not a kernel because it's not a homogeneous system, but it's related to the kernel. That's why the kernel is important. As a set, the solution set would be, again, Z is free. I already said what the solution would be. X would equal Z. Y would be negative 2Z plus 3. And Z is just itself. Collection of all such vectors such that Z is a real number. That's an infinite set. Z can be any real number. There's infinitely many solutions. Yeah, with situations like this example, usually with the right-hand side, it's inconsistent. There's no solutions. But if there is a solution, there's actually infinitely many. You can write that vector as a linear combination. Z times the vector 1, negative 2, 1, plus the constant vector 0, 3, 0. As Z varies over real numbers. That is not a kernel, not a null space of the matrix, but it's related to the kernel. Essentially, this part is the kernel. But that non-zero constant vector takes that kernel and translates it. If you were going to draw this solution set in three-dimensional space, attempt to draw it, and I'm probably not going to get it right here. Oh, I suppose I could try to get it right. So it's going to be a line because it's one-dimensional because there's just one free variable. If there's two free variables, then it can be two-dimensional. It's a line parallel to this vector. Where is that vector? 1, 2, negative 1, 1. Negative 2, 1. A vector about like that. It's parallel to that vector, but it doesn't go through the origin. This constant vector 0, 3, 0, which would be over here, shifts the line so it's not through the origin. The line itself is parallel to the red vector and also goes through this point here. So it would look about like this. That line that's supposed to kind of come out of the screen at you here and go into the screen over here is the solution set of the system of equations corresponding to this augmented matrix. If this line were parallel but going through the origin, that would be the kernel of A. But because the system's non-homogeneous, it's got to get translated, so to speak, and not go through the origin. It's no longer a kernel, but it's still a solution set. Does that make sense? Can I clarify that? How's this related to differential equations? Very much related to differential equations, the kind of stuff you've been doing recently, in fact, with linear equations. You've had two methods. You've had integrating factors. You also had fancy guessing, educated guessing, the method of undetermined coefficients. And what have you been doing when you did the method of undetermined coefficients? You've been thinking about the corresponding homogeneous equation. That's like thinking about the corresponding homogeneous equation here. And finding YH, general solution of that homogeneous equation, that's like finding the kernel of A, or the linear transformation. Because you had 0 on the right side, just like in finding the kernel of the linear transformation, 0 is on the right side. And then you found a particular solution. That's like, for the non-homogeneous equation, that's like the constant vector here. And then you added them. It's the exact same thing in just a different setting. Write it down here. Let's do it. Quick example. Say you have dy dt plus 5y equals e to the negative 2t or something. The corresponding homogeneous equation is make that right-hand side 0. This is your original equation, non-homogeneous. That's the equation you want to solve. To solve it, you consider the associated homogeneous equation. Because it's easier to solve, for one thing. You can solve it by guessing. You can rewrite it in this form, dy dt equals negative 5y, and guess the answer. The answer has got to be an arbitrary constant times e to the negative 5t. Those are the functions whose derivatives are negative 5 times themselves. That's your YH. Then you guess your particular solution for the original equation. Educated guessing, you see the right-hand side is e to the negative 2t. If there's going to be any chance of a function being a solution, it's got to involve e to the negative 2t. So you do your guessing and say, okay, yp, a particular solution, is some constant times e to the negative 2t. You got to solve for a, find y prime, plug it into the differential equation. What's it going to simplify to? You're going to get a negative 2a and also a 5a is a 3a, e to the negative 2t. I want to set that equal to the right-hand side. I want those to be equal for all t. So 3a has got to equal 1. So a is 1/3. So yp is 1/3 e to the negative 2t. And then your general solution of the original non-homogeneous equation turns out to be YH plus YP. C e to the negative 5t plus 1/3 e to the negative 2t, which you can then use to solve initial value problems. This is your solution set, so to speak, where C can be anything. This part of it is like a kernel of a linear transformation. What's the linear transformation? I'll come back to that. This thing is a particular solution. It's like a constant vector. Can you draw the solution as like a line in space? Well, not in the usual way of thinking about space, but maybe there's a new way to think about space where we can. Is this the only way to think about three-dimensional space? Actually, not necessarily. Turns out you can sort of visualize this as actually a line. How could it be a line? It's a line in what's called the function space, where the points are not ordinary points, they are functions. This is getting really weird. Even though it's weird, it's what people do. You pretend these functions, e to the negative 5t and 1/3 e to the negative 2t, are points in some function space. And C can be any real number. This traces out a line in that function space. What? I am being serious. I am not joking with you. Is this a useful thing to do? Yes, because it's useful because it unifies things by analogy. That part's the kernel of a linear transformation. What linear transformation? This one. Wait, I thought that was a differential equation. Yeah, but it's also a linear transformation. Well, okay, the entire thing is the differential equation, but this left-hand side is a linear transformation. But wait a minute, I thought linear transformations are functions. Am I saying the solution is the linear transformation? No, I'm not. I'm saying this expression as what's called a differential operator is the linear transformation. Here's the last point, and then I'll let you go. What does that mean? This expression, dy dt plus 5y, can be thought of as a function in its own right. What kind of function? Give me an ordinary function, well, like c e to the negative 5t, differentiate it and add 5 times itself. If I plug in c e to the negative 5t into such a thing, if I differentiate it and add 5 times the function itself, I will get 0. This will be an element of the kernel of this linear transformation. These are really wild and crazy thoughts, but this is where we're going. And this is, at the moment, the main connection between differential equations and linear algebra. Now, you know from the first lecture that there's other connections related to skew coordinates. That comes a bit later, a couple weeks from now.